Hello students, welcome to video lecturing class on dynamics of motion subject. So in the last video, we have studied about the gyroscopic effect on the aeroplane and what are the different cases, all those things we have studied. So today we will try to solve one of the simple problems. So here is the statement, the first one. An aeroplane makes a complete half circle of 50-meter radius towards left when flying at 200 km per hour. The mass of rotary engine and propeller is 400 kg, with the radius of gyration is 300 mm. The engine runs at 3000 rpm counterclockwise direction when viewed from the rear end. To determine the gyroscopic couple and its effects on the aircraft. So before, as I used to tell you, before starting with the actual solution, first you need to list the given data. So first we'll try to list out the given data. So the first one is, he has given the radius, that is capital R, equal to 50 meter, and he has given speed, that is velocity, is 200 km per hour. So we need to convert this one into meter per second. So it will be 200 into 1000 will become meter, divided by 3600, that is 3600, it will become per second. So together I will get it as 55.55 meter per second. And the mass M is given as 400 kg, and the radius of gyration is given K as 300 mm, so it will be 0.3 meter. And he has given the speed, that is capital N, as 3000 rpm. And we know the equation for the gyroscopic couple, that is G equal to I into omega P. It's not W, you have to read it as omega. Okay, so here I can be given by M into K square, and this omega can be calculated by 2 pi n by 60, and omega P is precision angular velocity, you can get it by V by R. So here in this equation we know all the values, that is M he has given, K he has given, N he has given, V he has given, R he has given. So we need to substitute these values to get the gyroscopic couple. So for calculation you will get G as 12,566.37 Newton meter. So remember this unit for the gyroscopic couple is Newton meter. So here we have calculated the gyroscopic couple. Now we need to analyze its effect on the aircraft. So moving further, so to analyze the effect of gyro couple on the aircraft, always it is necessary to you need to draw this diagram. Okay, so this is the top view and this is the front view, and here in this problem he has given that the rotor is rotating in counterclockwise direction when you view from the rear end, that is from the tail. Instead of viewing from the tail end, if you are viewing from the front side, that time it will look like the rotor rotation will be clockwise direction. So always remember, in one direction, viewing direction, you keep it as in one end, that is either from the back or from the front. So based on that you need to analyze the rotation of the rotor, that is the direction of the rotor. So here, according to the given condition, the rotor is rotating in counterclockwise direction when you view from the rear end. So this is the angular momentum vector. So initially it was at O to X. When it takes the left turn, that time it will change from X to Y, and this is the reactive gyro couple. So for this kind of thing, the effect will be, it will dip the nose and raise the tail. So this is the effect of the gyro couple on the aircraft. Now moving further, the second problem, the statement is, an aeroplane make a complete half circle of 40 meter radius towards left when flying at 175 km per hour. The mass of the rotary engine and propeller is 400 kg with the radius of gyration as 300 mm. The engine runs at 2500 rpm clockwise when viewed from the rear. Find gyroscopic couple. What will be the effect if the aeroplane turns towards right instead of left? Okay. So first we list out the given data. R is 40 meter, V is 175 km per hour. After conversion, it will become 48.6111 meter per second. Mass M is 400 kg, and the radius of gyration is 0.3 meter, and speed is 2500 rpm. So gyroscopic couple, for that we have the equation G equal to I into omega P, where I is given by mk square and omega is 2 pi n by 60 and omega P as V by R. So after substitution of these values, we will get gyroscopic couple as G equal to 11,453.72 Newton meter. So now to analyze the effect on the aircraft, so here he has given one condition: if the aeroplane turns right side instead of left side. Okay. So when we were viewing from the rear end, so it is the rotation of the rotor is in clockwise direction. Okay. So for the left turn, this is the direction, and for right turn, this is the direction. And if you draw the angular momentum vector for both the condition, so if it is taking left turn that time, this is the initial condition, initial position before turning. After turning, it will shift to O to Y. So in that case, it will raise the nose and dip the tail. But here he has given that instead of left, if it takes right turn, that time your angular momentum vector will be like this. So here this is the initial condition and this is the final one. So in that case, it will dip the nose and raise the tail. So that is the effect. So only the effect of gyro couple on the aircraft will change here. That is, if it is taking the right turn when the rotor is having clockwise, when you are viewing from the tail end at that time, and it will raise the nose and dip the tail. But instead of left, if it takes right turn, that time it will dip the nose and raise the tail. Next, we will move to the gyroscopic effect on ship. Okay. So before starting with the actual study of the gyro effect on the ship, so first we need to understand some of the important terms connected to ship. Okay. So they vary, as you can see in this figure, named it as bow, stern, and port, and this one as starboard. Okay. So bow is nothing but the front portion of this ship. Okay. And stern is nothing but is the rear portion of the ship. And with respect to the sailor, the right side of the ship is called as starboard. This is. And with respect to the sailor, the left side of the ship is known as port. So in ship, gyroscopic effect may be represented under the three cases. That is, the very first one is steering, pitching, and rolling. So in case of steering, the basic definition of steering is the turning on one side when viewing from the top end. Okay. So here also, we'll have the conditions. The first condition, that is case number 1, is assume the rotor turns clockwise when viewed from the stern and the ship takes left turn. So assume the rotor turns clockwise when viewed from the stern. When you are viewing from the back end, that time the rotor is rotating in clockwise. But for the same rotation, if you are looking from the front end, that time the rotation of the rotor will be in the direction of counterclockwise. Okay, and the ship is taking left turn. So what will be the effect? You need to analyze. So here the angular momentum is represented like this. So this is the before turning and this is the after turning, O to Y. And this is the reactive gyro couple. So its effect will be, this couple will act in vertical plane and it tends to rise the bow and dip the stern. So it will tends to rise the bow and dip the stern. Similarly, the second case, if the rotor turns clockwise, the rotation of the rotor condition remains same. When viewed from the stern, the direction of viewing is also same, and the ship takes right turn. So instead of left, it takes a right turn. So that time the angular momentum can be represented by this vector diagram. So here the effect will be Again, this couple will also act on vertical plane, and it will tends to dip the bow and raise the stern. So just the effect will be reverse as in case of the left turn, provided all the conditions remains same. Now the third one, that is, assume the rotor turns counterclockwise when viewed from the stern and it takes the left turn. So here in this figure, so this is basically for the rotor direction when it is rotating in the clockwise direction. That time left turn is like this and right turn is like this. If the rotor is rotating in counterclockwise direction, just you need to reverse these directions for left and right. You need to remember that one. So the case 3 is when the rotor turns clockwise direction, counterclockwise when viewed from the stern, and ship takes left turn. So this is the angular momentum vector diagram. So effect will act on the vertical plane, and here it will tend to dip the bow and raise the stern. And the fourth case is again the rotor with counterclockwise direction, but instead of for left, it takes a right turn. So the angular momentum vector diagram will be this, and the effect will be the couple will act in the vertical plane, and it tends to raise the bow and dip the stern. And for this also you have to calculate the gyroscopic couple. For that you can use the same equation as in case of aeroplane. So that is G equal to I into omega P. So all the terms remain same. The only difference is here M will be mass of the rotor in kg, K is radius of gyration of the rotor, N is speed of the rotor, V is the speed of the ship, and R is the radius of curve. That should be in meter. Now the second element is pitching. So pitching is the moment of the ship in vertical plane when weaving from the front. That is, pitching is limited angular motion of the ship about its transverse axis. Okay. So here also we will consider 4 cases, that is 2 cases for clockwise and 2 cases for counterclockwise. So assume that the first case is, assume that rotor turns clockwise when viewed from the stern and bow ascends, that is bow is rising here. So here these directions are for when the rotor is in clockwise direction when you are viewing from the rear end. Okay. If the rotor is rotating in counterclockwise when you are viewing from the rear end, that time you need to reverse these directions. Bow rising will be this way and bow lowering will be this way. Okay. So right now the rotor is having clockwise, so bow rising will be towards downside and bow lowering will be towards upside. So the angular momentum vector diagram will be this. This is before turn and this is after turn. Okay. And the effect will be the couple acts in horizontal plane here and tends to turn the bow towards starboard, that is right turn. So here the couple is acting on the horizontal plane because this motion is limited towards the transverse axis, whereas in the previous case, that is in steering, it is about the longitudinal axis. Then the second case is rotor rotates in clockwise direction and bow is descends, that is for the bow lowering effect. So the angular momentum diagram will be this, that is this is before the lowering and this is after the lowering. So effect will be again couple acts on the horizontal plane and it tends to turn the bow towards port, that is left side. Next, the 4 cases. Assume the rotor turns counterclockwise when viewed from the stern and bow ascends, that is for the bow rising. So the angular momentum vector diagram, this is before the rise and this is the after the rise, and this is the reactive gyro couple and this is active gyro couple. So here the effect will be, it will act in the horizontal plane and it tends to turn the bow towards the port side, that is for the towards the left side. In the 4th case is when the rotor turns counterclockwise and bow descents, that is for the lowering. So this is the angular momentum vector diagram. So again the couple will act in the horizontal plane and tends to turn the bow towards starboard, that is will take the right side. So the pitching of the ship is usually considered to be takes place with simple harmonic motion. Okay. So if the theta is the angular displacement of the axis of the spin after t, that is time t, and pi is the maximum angular displacement of axis of spin, then we can write theta as theta equal to pi into sine into omega 1t, where this omega 1 is angular velocity of simple harmonic motion, which is given by 2 pi by tp, where this tp is time period of simple harmonic motion. So therefore differentiating this equation, so d theta by dt equal to pi into omega 1, because this is the constant, omega 1 is the constant here, cos of omega 1t into, so if we put together we can write it as omega p, where, and this precision velocity will be maximum when this cos of omega 1t equal to 1. Maximum angular velocity of precision, that is omega p max, can be given by pi into omega 1, which is equal to pi into omega 1, we can replace it by 2 pi by tp, that is time period, where in this equation this pi should be in radians. And then the next one is the maximum gyroscopic couple during the pitching, that is G max is given by I into omega p max. Again here also you have to use the same equation, only difference is while writing the equation for omega p, there you used to write it as V by R. So here it is pi into 2 pi by tp, and the unit remains same. And for maximum acceleration, differentiating again this equation with t, d square theta by dt square equal to minus pi into omega 1 square to sine of omega 1t, which is equal to alpha. So that is alpha max is given by minus pi into omega 1 square. This will be maximum only when the sine omega 1t equal to 1, which is equal to minus pi into 2 pi by tp whole square, because this omega 1 is given by 2 pi by tp. Now the third one is rolling. So here basically this rolling is the limited angular motion of the ship about the longitudinal axis. So the gyroscopic effect will be present only if the axis of precision is perpendicular to axis of spin, but in most of the cases, that is in rolling, axis of precision is always parallel to the axis of spin. Hence we have to avoid the gyroscopic effect on the ship due to rolling. So we can calculate the gyro effect, that is gyroscopic couple, G equal to I into omega p of rolling. Here you have to use the same equation as that you are using for the steering mechanism. Okay, so this is the effect of the gyroscopic couple on the ship. So in the next video, we'll try to solve some of the problems and we'll try to analyze the gyroscopic effect on the ship. So if you have any doubt, you can leave the comment in the comment box. Thank you.